Good afternoon, everyone. I would like to welcome you to today's session on a look inside the BITZER Compact Screw Compressor. Our presenter, Phil Boudreau from BITZER, will give you a technical overview of the BITZER Compact Screw Compressor, along with the internal subsystems that make the compressor a great solution for commercial and um, industrial cooling heat pumps and process cooling systems. Moving on to housekeeping, you will notice on the control panel of your screen the Q&A feature. Please use the Q&A feature to ask your questions at any time during the webinar. They will be addressed at the end of the session. Also note, this webinar is being recorded and the recording will be shared with you following the session. Now, we welcome Phil.
Good afternoon, everyone. Welcome to today's session on compact screw compressors. We just have just under an hour to cover the materials. So this is actually a slightly trimmed version of the usual compact screw compressor seminar. Nevertheless, we do have a lot of information to cover here. So getting into the topics that we'll cover, general application, compressor construction. We'll discuss capacity control. This is where we'll talk about slide valve control versus variable speed type control, economizing of a compressor for performance, additional capacity and efficiency. So at first, I'll say the compact screw is known as it's referred to as a compact screw because basically all screw compressors require they pump a good volume of oil, and this is necessary in order to maintain a good seal for compression. With a lot of screw compressor designs, the oil separator is separate. So when we say compact, we're actually referring to design that has a motor, compressor, and oil separator all combined into one package. Similar to all of the BITZER screw compressors, in fact, open drive semi-hermetics, the compact screw compressors are of the twin rotor design type, which we'll take a closer look at when we look inside a cutaway, graphic cutaway. The slide valve for capacity control, we'll go through how, what it looks like, how it's controlled, the different ways of controlling it. The fact that the motor is VFD compatible. In fact, this is really the case with all of the BITZER compressors. They all have a VFD compatible motor built in. Onboard temperature monitoring. Now, this is really to monitor your discharge and oil temp, and also the motor winding temperature, just to ensure that something's not going wrong in terms of single phasing, motor overload, or what have you. These compressors are also available with different VIs for different applications, which I'll talk about that in a few minutes. So there's four main, we'll say, categories or body styles for the compact screw. We have the 65, the 75, 85, 95. Of course, they get larger, progressively larger as we get into the higher numbers. So just to summarize all of this here, overall, your range of displacement is 5,830 cubic feet per hour, up to a maximum here of 47,710 cubic feet per hour at 60 hertz. And if you want to relate this to a horsepower, that's a nominal 35 horse to 320 horsepower range. So compact screws are used in air cooling type equipment and liquid chillers. So comfort cooling applications, heat pump applications, process cooling, drying, many applications can use a compact screw compressor. In fact, we use the compact screw quite a bit in retrofit applications. Earlier compressors that maybe are difficult or impossible to replace or just take a long time to source. We'll use these in many of these types of applications where we'll replace reciprocating compressors, as was done at this particular site here. Here we have a comfort cooling chiller, and to the left here we have this is actually for a makeup air chilled water system. So, and this is just the rendering for this model. So in the CSH product line, there's basically 21 models. And I mentioned the range of displacements and horsepowers. You can see up here the refrigerants. And there's some others here. We didn't try and list them all. But these are the refrigerants that can be used in these types of compact screws, generally speaking. And there is also a CSW series, which has a lower VI or volume index. And again, we'll talk about that in a few minutes. And that's really designed for, say, water-cooled condensing or low condensing temperature applications. So let's take a look at the internal construction of the compact screw. First, we have a motor, because this is basically a semi-hermetic refrigerant-cooled compressor. So we have our motor over here. We have the terminal block, which enables connections for a cross-the-line start, part line start, and in some of with the larger motors, I think over 180 horsepower or so, Y delta start. Then we have our male rotor. The male rotor is connected to the motor and driven by the motor directly at a speed of approximately 3,500 RPM. And then we have the female rotor adjacent to the male rotor there. We have a 10 micron oil filter. So these are some of the main components to get started. Taking a closer look at the motor, we use a high efficiency 2-pole, so hence the 3,500 RPM. Slide fit motor. It's slide fit because it's actually got a stator pin, a lock here. This can be removed. Terminal plate can be removed. Then the motor can be replaced if needed. Variable frequency drive and soft starter compatible motors, as I mentioned before. And again, these can be wired for direct across-the-line start. So across-the-line starting is basically what you would generally do with smaller motors anyways. And then if you're going to wire for a VFD or a soft starter, then in these cases, of course, you would wire for across-the-line starting or direct online starting as well. Part line starting enables a reduction of amperage. So for example, regular part line start, where you've got 2 windings here, you energize the first winding. Basically, you've got 2 sets of stator windings inside the compressor. One winding set's energized. Half a second later, the second set is energized. And that's a maximum of a half a second, by the way. That'll result in a reduction of amperage of approximately 35% reduction from your locked rotor amperage. Then there's the Y delta approach, where we can reduce the amperage to approximately 35%. And this is give or take, say 5% of the locked rotor amperage. And note, there's a little more timing because what we're doing is rewiring the compressor on the fly, basically using the 3 contactor method. Getting back to our construction, we have a suction service valve, which is standard on the compressor. The discharge service valve, another standard component. So your refrigerant flow, refrigerant comes into the back end of the compressor, we'll call it the motor end, travels through the motor to extract heat from your motor windings, and through the rotor, there's some bores, so holes drilled through the rotors that allow refrigerant passage through them. Refrigerant then enters the screws at this point here, okay, and they turn away from each other. And gradually, through a number of contiguous pockets, this refrigerant is continually compressed until it reaches the discharge pressure, where it is then discharged into the oil separator here. Because screw compressors do not have active working valves inside, a discharge check valve is required. So this is because when the compressor shuts down, you have a high side pressure that exists here and a suction pressure on this end. And if we were to just have this through piped, no check valve, we've also got the system exposed to, we've got the high side pressure after the compressor and the, everything upstream of the compressor and the suction line. So without the check valve, everything would equalize. So essentially high side refrigerant would continue to travel back towards the suction line until the pressures equalize. So we don't want to have that, hence the purpose of the check valve there, or the reason for it. So we have the oil service drain or service valve here for draining the compressor, for charging the compressor. There's also another port generally under the motor barrel here. So if you're doing a full oil change, you can drain the oil out of the compressor. Any residual oil that may be sitting in the bottom of the motor barrel here, you can drain that out as well. There's an oil heater here. Very important that the oil heater is energized several hours, probably 12 hours or so, or a good day prior to starting up a compressor. And this is the case with semi-hermetic. This is the case with all compressors, in my opinion, particularly when you're running HFC refrigerants and HFC, HFOs, which we don't see much of here yet in North America because the codes and standards do not permit that quite yet. But it's very important because the heater limits the amount of refrigerant that's going to be in the oil. More refrigerant in the oil means less viscosity, means less lubrication, and reduced compressor life. So energize those heaters and give them enough time to start up. Now, this is an earlier type diagram. Most of the basic features are here. But in the earlier models, we had a mechanical float. So there's a oval flange here. You'd remove and put the float in there. Nowadays, we actually use a optical type oil level controls. So in the past, we had a sight glass here. In the newer models, we actually have two sight glasses, an upper and a lower. So generally your low level, the lowest sight glass position would be used for a low oil level limit switch, okay? So your nominal oil level, generally you wanna see it up in the upper sight glass here while it's running. Getting back to construction, we have the oil separator basically operates based on three, we'll say approximately three separation techniques. So first we have impingement. As I mentioned before, with the refrigerant, there's a lot of oil leaving the screws, and we need to collect this oil and return it back to the compressor so that it can be used. Of course, we don't want to be pumping this out into the discharge line because now this is going to interfere with heat exchange throughout the system. We don't want to have too much oil in the evaporators and condensers and so forth. So the oil laden refrigerant leaves this pipe here. There's different designs depending on the compressor configuration, the body class or body style. But we have impingement against the shell. There is some centrifugal force that takes place due to the positioning of the discharge of this pipe here. And also there is a final stage, we'll call it demisting, which basically is another form of impingement, I guess you could say, but also allows for some coagulation of the oil as the droplets all collect together and drain down into the bottom here. You can see the light brown shaded area here indicates that this entire oil separator along to the sight glass is actually got a good layer or level of oil in there. So moving on, a screw compressor requires absolute precision when it comes to the layout of the rotors and their distance from each other. The distance between the rotors and the housings is extremely important. These clearances are maintained using good quality bearings. So in this case, we have two types of bearings. The first being the roller type bearings, basically to support the shaft movement up and down, side to side. And then there's the axial type bearings, which prevent axial movement, specifically towards the suction. When the screw compressor starts up, the discharge pressure, of course, is increasing. Sorry, I'll back up a bit here. Discharge pressure is increasing on the discharge end, of course, and we've got a low pressure at the opposite end. So the screws tend to want to move this way towards the suction. And if we don't limit the movement, then we're going to have a problem where these rotors go back and come into contact with the suction spacers. And trust me, that's never a good thing. So if you want to take a closer look at the two types of bearings used, these are the radial bearings to basically support, again, the rotors from the radial type movement, and the axial type bearings to prevent the axial movement, specifically in the direction towards the suction line. or the suction of the compressor. Now, this is actually a line drawing, if you will, of a semi-hermetic screw compressor. I just put this here to illustrate a point. So again, we have a discharge in the, or a check valve in the discharge of the compressor. And then there's this, there's a component in here known as the pressure flange or discharge flange, and the clearance between the rotors and that flange is very minor. And if I was to just guess, I'd say it's probably in the neighborhood of a 1,000th of an inch or something like that. And basically, it's just enough room to allow for a film of oil. Anything beyond that, of course, is going to contribute to leakage in that. So, and if you have it too close, then we don't have enough room for the film of oil. So the setting of this clearance is absolutely important. And we're not really going to get into how you do that, but here's a slide that basically shows it all. Basically, what we're doing is just moving the rotor back and forth and looking for a maximum deflection that's in accordance with the maintenance, the BITZER maintenance manuals, and that's typically how it's done. And this clearance is extremely important because you don't want those rotors locking up, of course. We don't want them coming into contact with the suction spacers and that sort of thing. And note that screw compressors, they're designed to operate in that one direction. If you turn a screw compressor incorrectly, the wrong direction, you can destroy it in a very short period of time. So we want to be careful at startup to make sure that the screw is turning in the right direction. Generally, what's involved there is, of course, you would always refer to the instructions for starting up the compressor. But generally, what you'll do is close off the suction service valve completely, open it up one turn, and just give the compressor, just allow it a split second just to turn over, and having it with a gauge on a low pressure port of the compressor will enable you to look for that gauge deflection in a downward manner. So we want to see that pressure drop. That'll indicate the compressor turning in the right direction. If it starts to increase, or more commonly, you don't see it do anything, maybe it just flutters a little bit, that's an indication that the two of the wires need to be reversed so that you can reverse the rotation of the compressor, but then repeat the test again, definitely, just to be sure. One additional feature of these compressors is we have the vented bearing chamber here. So the bearings, particularly on the discharge end of the rotors, are isolated from the high pressure refrigerant. However, the oil traveling through the compressor, throughout the compressor rather, contains a fair amount of refrigerant, and just at a necessity, and it's just the way it is, whenever you expose refrigerant at a high pressure to oil, the oil will absorb some refrigerant. So the idea here is once the oil gets into the bearing chambers, we reduce the bearing chambers to a lower pressure, and what that allows for some degassing or off-gassing of the oil, if you will. And this in turn increases its viscosity, allowing for better lubrication and longer compressor life. Taking a look at capacity control, the BITZER compact screw uses 4 solenoids for capacity control. So this gives us a couple of options. And there's some flexibility with the options too. There's actually several different ways you can control them, but basically using these 4 solenoids, we can control based on a fixed step mode where we can operate the compressor at steps 25, 50, 75, and 100%, or we can drive the slide valve anywhere in between, hence the term infinite, using just 2 solenoids, for example, and pulsing those 2 solenoids. Inside the compressor, we have the rotors that I mentioned, the twin rotors, and then there's the slide valve that actually makes up part of the housing. And I'll show you an actual photo of it, so you'll have a better idea how it works. But for now, I just want to explain how the slide valve control works. So we have the slide valve, and you can see there's a gap here, okay? So this slide valve is in a reduced capacity mode at the moment, okay? In fact, I can see here it's at the 50%. So the way this works is there's one loading solenoid and 3, if we could call them this, unloading solenoids. These are simply vents to the suction. Okay, so when we want to load the compressor, we simply energize CR4. CR4 then accepts high pressure oil from the high side of the compressor, the oil reservoir, fills up this chamber, in turn pushing the slide valve to the left and closing up this gap here. Once this gap is completely closed, now we're using the full effective length of the rotors to achieve compression. This is when the compressor is operating at maximum capacity, of course. If, on the other hand, we want to operate the compressor at a lower capacity, we're simply going to vent some of this oil back out of the control chamber here and into the suction. And with the assistance of the spring will also push to allow that slide valve to return. And generally on startup, this slide valve, you want to have that set so it's in the most unloaded position here, which would be the 25% position. So you can see here in the chart, there's the different modes for controlling your start unloading or your 25% mode, which is your minimum step, would be achieved simply by energizing CR3. Okay, and that just allows anything that's in that control chamber to be vented back to the suction with the assistance of the spring pressure behind the slide valve. If we want to load that up, then you can see, at 50%, you would energize CR2, and then we would pulse the loading solenoid because we need something to drive it to that position. If we want to move it to 75, we just simply energize CR1. As you can see in the control chamber, CR1 is way over here compared to CR2 and then CR3. So the more we want to load it, okay, the closer we get up to CR1 for 75%. And then eventually, none of these solenoids here, these vent solenoids, will be energized. If you want to run 100%, then we're simply going to either pulse CR4, or in theory, there's no reason why it couldn't be just energized, but generally it'll be pulsed as part of the operating sequence for all unloading steps. Infinite capacity control, though, on the other hand, we really only need to use 2 solenoids, and there's different ways you can do this, but I'll give you one example here, where we're going to use CR3, which is your minimum capacity solenoid here. Okay, you can see its connection to the control piston is way at the end here, and CR4. So we have an unloading solenoid basically and a loading solenoid. So if we want to simulate loading from 25% to 100%, it would look something like this. Note the gap is closing, and now we're loaded. So we have the full effective length of the rotors being used to compress refrigerant from low side pressure to the high side pressure. In order to simulate unloading from 100% to 25%, similar procedure, we just changed the solenoid that we're pulsing. Now we're going to pulse CR3. And could you just energize CR3? Yes, you could, but the idea behind pulsing it is pulsing gives you control over the change in which that slide valve, or the speed at which that slide valve moves. Generally speaking, in systems, we don't really want anything changing too quickly because you've always got regulators and expansion valves and everything else that are always trying to keep up. And slow change is always better, in my opinion, because it gives everything a chance to keep caught up, basically. So looking at these 4 capacity control solenoids, on the compressor, it looks like this. And in terms of their locations, our loading solenoid CR4 is down here on the lower right. And then we have CR3 as our 25% at the lower left. And then we have 50% CR2 upper right and 75% solenoid upper left. And of course, again, if you want to run 100%, neither CR1, 2, or 3 are going to be energized, only CR4 to drive that slide valve in this direction to load that compressor up. So as the thermostat is calling and satisfying, or if it's an analog signal, it's changing. Okay, so we've got the control band here. We call for cooling, and then we're satisfied. we can cycle the solenoids here. So we have a demand for capacity at this point, and then we have a reduced demand for capacity over here. So looking at the in the operating instructions, the application manual for the compressor, there's guidelines in terms of setting this up, but initially the recommendation is 0.5 seconds up to a maximum of 1 second for your pulse times, which is your on time for CR4 and CR3. And then depending on the system inertia, okay, basically how much that fluid temperature or air temperature is changing over time, then the timings T2 here and T4 can be adjusted. So really depends on the system. So there is no real out-of-the-box type control solution that could serve this. And some of the manufacturers that use the compressors, I mean, over time, they adjust their algorithms accordingly to their system designs, but sometimes they have to tweak them also for various applications due to different load requirements and what have you. One thing we do have to be aware of, as with a lot of compressors, just because you can unload a compressor all the way down to the minimum doesn't mean you should. It really depends on the compression ratio or the operating conditions that you're operating at, refrigerant type that you're using, the compressor model, perhaps in some cases. So we do have to be aware of this table or this chart, which can be quite confusing and intimidating when you first look at it. But just at a high level, I'll show you how this works. This would be your 25% line here. That means anything to the right of that or to the lower right, you can operate that compressor basically down to 25%. The next line means that you can operate the compressor down to a minimum of 50%. You can't go any further than that. You can't unload below 50% because your compression ratio is getting higher and higher. At this level, the compression ratio, along this line, compression ratios are getting higher and higher. So you can only unload by 25% down to that 75% capacity level. And then anything beyond that line, you can't even unload the compressor. So we do have to be aware of this, and this has to be programmed into the control systems in order to make sure that we're not pushing the compressor outside the envelope. Specifically, what's going to happen is you're going to start overheating, and compressor's going to trip, and you'll have some problems like that. And you'll note there's this small section here that shows that the maximum is 75%. Basically, what this is saying is that we're operating a fairly high evaporating temperature, low condensing temperature. Mass flow rates are so great. We don't want to, aggravate that by running at 100%. So the idea is to back it off. And I guess to some extent, this is to limit oil carryover because the oil separator is designed for a certain duty. And even solubility of the oil. When you're running low compression ratios, your heat of compression is going to be lower. So it does have an impact on lubrication as well. So with the slide valve, with screw compressors, I should say, because we have a number of contiguous pockets that are in series, these pockets operate independently of the discharge, meaning that in a reciprocating compressor, for example, you compress that refrigerant, it works its way up to the discharge pressure. In a helical rotary type screw compressor, what happens is you've got a number of pockets that are compressing the refrigerant. It's actually possible to overcompress the refrigerant. So the pressure inside the rotor profiles exceeds the pressure in the discharge line. And when that happens, we end up with overcompression. So you can see here that P2 would be our regular high side, or we'll call it condensing pressure. Okay, and we've compressed up to that, but past that inside the rotor profiles. And then once the rotors open to the discharge port, that high pressure refrigerant now actually drops to the condensing pressure, which of course is inefficient and results in this additional power consumption. And similarly, you can actually have under compression in a compressor for a similar reason, and then you're only using part of the screws, and you've actually got discharge pressure at times backing into into the rotors, which may seem very difficult to imagine, but under compression and over compression are two very possible things that, well, they will occur with a screw, particularly when it's not designed to compensate for different pressure ratios. Now, in the case of under compression, what that means is you're going to have lost work that compressor could have done, but that's not available anymore. And there is the formula for that, by the way. So, and yeah, I shouldn't have passed this slide too quickly. It's quite important, actually. So what is volume ratio, or volume index as it's referred to? The ratio of the volume of the gas trapped at the start of the compression process to the volume of the trapped gas where it begins to open to the discharge port is known as the compressor's volume ratio or volume index. So if you take the volume of the refrigerant at the discharge port of the compressor and divide the volume of the refrigerant at the suction end of the compressor divided by the volume of the refrigerant in cubic feet per pound, just a specific volume, okay, divide the volume of the discharge gas into that, we get a volume ratio or volume index. And you want your compressor to match that pretty good, or the compressor needs to be able to adapt so that it can operate efficiently in that range. So the reason why I'm telling you all this is since we're talking about capacity control, and I apologize for this photo. I take full responsibility for it because actually I'm the guy who took the photo. But it highlights something interesting with the slide valve. If you take a look at, this is the discharge end of the slide valve. You can see that it's actually machined out, okay? And if you can see it here, this part of the slide valve will allow for a somewhat smaller discharge port here. It may be difficult to imagine, but the slide valve is part of the discharge port, okay, here. And then on the pressure flange I mentioned before, your discharge port is on the discharge flange itself. So the slide valve moves into the discharge flange, and this port gets smaller as the slide valve moves towards it. Due to this, you can see that it gets larger as we get towards the center of the slide valve. And I apologize for this photo either. I just didn't have one. This is just a compressor I took that was open. Obviously, a compressor that's been in the field for some time. By the way, these are those suction spacers I was talking about. If your rotors move too far to the back, they're just going to start cutting into the suction spacers and making a mess. And well, let's just say at that point, it's pretty much game over, because once you start making metal inside that compressor and the rotors start picking it up, it's just going to start basically chewing everything up. So if you take a look at the slide valve, as I mentioned before, it actually makes up part of the rotor housing here. Okay, so it actually sits between the rotors. So your male rotor sits here, and then in the larger bearings, and then you've got the female rotor sits over here. Then the slide valve moves in and out. And as you can see, when the slide valve moves in this direction, this gap opens up here, and we start to basically eliminate some of the effective length of that rotor, or the rotors rather. Okay, and if I was to highlight it, it would look something like that. So there's your slide valve, and this will be connected to your control piston chamber, as I mentioned before, and we just slide that in and out to control the capacity of the compressor. Another way, another form of capacity control would be the use of a variable speed drive on a compressor. And in this case, we can operate compact screws from 25 to 60 hertz. So you've got a pretty good capacity control range. It would require basically a VFD, which takes your 3 sine waves that come into the VFD, and they're actually converted basically through rectifiers to a DC voltage, and then it goes through a transition circuit, basically stored where the voltage is stored in capacitors as a DC voltage, and then the output circuit is basically just taking that DC voltage and pulsing it to produce basically a quasi kind of sine wave to run the compressor. And one important thing to note about VFDs on compressors in general is compressors rather are constant torque devices. So it's important that the drive is configured, programmed, so that we do have a constant torque. And generally this means that your voltage to frequency ratio remains the same throughout the entire speed range, with a few exceptions. It's pretty typical to add a little bit more torque, meaning increase the voltage slightly when you're operating the minimum. Well, actually starting up the compressor is what I meant to say. It's also important to note that the VFD should never be used in conjunction with the slide valve. Okay, keep in mind this is a refrigerant cooled motor, and if you're driving the slide valve down to, the worst case scenario, let's say we're driving that down to 25%, and then you're going to slow the compressor down to 25 hertz. We get to a point where oil lubrication becomes an issue. We have insufficient refrigerant to cool the motor. All sorts of problems. So although BITZER does actually produce compressors, which I didn't include in this presentation due to the limited time slot we have, but another frame size, if you will, of the compact screws is the CSV series, and the CSV have an integrated VFD and slide valve and VI control, and these things can all be controlled together using a special BITZER controller, an IQ module that is used to accomplish that. But the CSH and CSWs, either using a slide valve or using a VFD, never both. In order to size the drive, we recommend using at least the maximum operating amps for screws, but our recommendation is to take the maximum operating amps and add 10%. So you've got a little bit of safety factor. A little bit of safety factor is always good. We need to allow for pull down, everything else. But the maximum operating amps of that compressor is basically the maximum amperage that compressor can draw. So it's tied to, you could say, the maximum power input to that motor as well. That motor can only do so much. If you push it too far, it's gonna overload. So that point at which the motor is fully loaded up would be considered like the MOA. That's a common term used overseas. In other countries, here in North America, MCC is more common. MCC and MOA are you could say, I would say they're fairly similar in terms of the actual value. But we use the MOA regardless for sizing compressors, or VFDs rather. If a contactor is being used, and this is generally the case with most of the VFDs installed on BITZER compressors, at least here in Canada, it's very important that that run command is removed from the VFD immediately when the contactor opens. And the reason for this is that when that contactor opens, if you haven't removed the run command, there's still some power existing in that drive, and it's going to start to drop off. And what'll happen is you're going to start to run into alarms. You could see an overload alarm, a low bus voltage alarm. That's the most common one. And also what you're doing is put a lot of strain on, there's these components known as metal oxide varistors at the inputs to the drives. And, they can take a bit of abuse, a few cycles of this, but you do this repetitively, you're eventually going to take those out, and then the drive's got to be either repaired or replaced. So, if you're using a contactor because it's a non-STO application, then you want to remove the run command. And an STO application just means safe torque off. Some drives actually have that ability to guarantee that drive will take the compressor off line in the event of a safety. So a high pressure control opens, or some critical safety like that, it needs to be absolutely guaranteed that the compressor is taken offline. So only a drive with that STO can do that, would be accepted to do that. Other drives you would use, you need to use the contactor. And then you just put the most critical safeties in series with that contactor coil. And then when that trips, you would have that would be your run command would be basically interlocked with that. So it stops calling immediately. And also note that there's a special compressor module required. And the reason for this is that normally with AC mains, we have a fairly clean 3 sine waves coming into the compressor. But when we put a VFD in between our sine waves and the compressor, the VFD reproduces the sine waves using a series of digital pulses. Okay, and the SCE1 standard module doesn't do the greatest job. In fact, sometimes it'll work and other times it doesn't. It's just not, it shouldn't be used whenever a soft starter or VFD are being used due to the different types of waveform forms that exist at the input to the compressor terminals. We need to use a module that can better see that. So I mentioned the SCE1, that's the standard module. With the VFD applications, soft starting applications, we definitely want to use what we call an SCE2 is the current number for it. Wires in exactly the same, functions are exactly the same. You know, it's monitoring motor temperature, and it's also monitoring your motor and oil temperature. In addition to that, it's monitoring phase. It's looking for phase asymmetry or rotation. If your phases are coming in the wrong order, then it won't allow the compressor to run. So economizing is actually our last topic. That'll be about all we have for before we close it off for questions. So economizing is a very interesting topic. There's a number of different types of compressors that allow for economizing, and screws are one of them. With a screw compressor, as I said before, because we have a number of contiguous pockets compressing refrigerant simultaneously, in this case, we can actually access the compression process partway through. So let's just say, just to pick a number for an example here, 25 to 30% of the distance, say from the suction end of the compressor in, we could actually inject a flow into that compressor there. So a side load, we'll call it, something like that. But we're going to use it in this case as an economizer. So your normal cycle would look something like this. Of course, these are red lines and my pointer's red too, so that doesn't help. But if we go back to the pressure enthalpy diagram here, we can see when we plot a cycle, it may look something like this. Doesn't matter what the values are. This is just to give you an example. So our actual net refrigeration effect that takes place in the evaporator is basically this much. The difference between, maybe 260 kilojoules per kilogram, in this case it's metric, to 150. Okay, so that differential represents the net refrigeration effect. This, of course, represents your power input. So in this particular case, if we were to introduce a second heat exchanger, or I guess a third, if you consider the evaporator and the condenser, we've got an economizer type heat exchanger. Basically, we just call it a subcooler because that's what it is. On one side, it's refrigerating expanded liquid, and that absorbs heat from your main stream of liquid going into the evaporator. And I'll show you the process in more detail in a moment here. But so what happens with your main liquid leaving the condenser is it's further refrigerated in the economizing heat exchanger or subcooler. Okay, and then that additional subcooling, of course, allows for additional heat absorption in the evaporator. So we're able to achieve more refrigerant in that evaporator for a given set of conditions. Now, in order for this to happen, on the opposite side of that heat exchanger, we have a refrigerant boiling that enters some intermediate point within the screw compression process where we compress the refrigerant. And that has to take place after the refrigerant is drawn into the suction end of the compressor, and then those rotors trap the refrigerant. It has to be after that point. Otherwise, the economizer is going to interfere with the suction vapor entering the compressor, specifically drive it upwards, which we don't want to do if we're trying to hold a certain evaporating temperature. So the compressor has an eco port on the side of it, or economizer port, where that refrigerant can enter the economizer port, okay? Because we need to have a destination for that refrigerant in order to keep the process going. That refrigerant then is mixed with the refrigerant from the evaporator, compressed, and sent to the condenser. Now, this slide may look like it indicates that economizing is free, and it's, let's just say economizing comes at a fairly low cost in terms of the power input and the few components you need, but power increase, or the power will increase because you're doing more work, that's for sure. But what you're getting in return for the additional power that's been absorbed is considerably more. Considerably more when you get into high compression ratio applications. And in my opinion, when you get into really high compression ratio, well, we'll call them freezers, or anything operating, compact screw compressors are not really low temp compressors, but we'll say medium temp, and then the lower temp end range of the medium temp, economizing just makes more and more and more sense. So looking at this graphic here, this will show the actual process here. So this is the standard process without economizing, where we have suction vapor entering the rotors, compressed to the condensing pressure here. When we economize, okay, and we can see here that there's the length of the rotor. We start at one end of the rotor, suction gas goes in, we compress, and it leaves the opposite end here. When we economize, as I said before, we inject refrigerant from the heat exchanger, an economizing type heat exchanger, into this point right here. Okay, and you can see where that process begins here. Obviously, that will be at a higher pressure. And as we know, when you operate a compressor at higher pressures, you'll get more mass flow, and generally speaking, more capacity for every kilowatt that you put into that compressor. So overall, your power input per ton of refrigeration, I'll say, will be less when you do that. So generally, well worth it. When you get into higher temp systems, you really have to kind of weigh out the pros and cons, the costs and what am I gaining for it and all that. But you can economize any system really, or any compact screw compressor based system. So it looks like this. Okay, so we have our screw compressor. Discharge gas, I'll just start at the high side of the screw compressor. And actually the graphic is kind of showing like a semi-hermetic compressor. With the compact screw, just keep in mind the oil separator is kind of incorporated with the compression process here. This is all a compact screw compressor here. There is no external injection line. This is just a graphic that I pulled from a semi-hermetic presentation that I had, since it lays it out quite nicely. So in the compressor, we compress and separate the oil, and then we have refrigerant leaving the discharge port of the compact screw, enters the condenser where it condenses. And then, this could be a water-cooled condenser. If it's an air-cooled condenser, you'll likely have a receiver after that. And then that liquid will travel to the evaporator, okay, where it will be expanded by the thermostatic or electronic expansion valve, which will maintain a superheat at that evaporator outlet. Business as usual here, back into the suction end of the compressor. So if it's a system that's designed for 105 condensing, if we factor in a little bit of subcooling, maybe you're running 100 condensing, something like that, 95 condensing. But when we enable a subcooling circuit like this, so what we've done is added a heat exchanger here. Note that it's piped in counterflow, so the main liquid going to the evaporator travels this way, and the refrigerant that is going to boil on the one side of the heat exchanger, most commonly a braze plate, from what I've seen. Okay, so that refrigerant will evaporate and travel through the heat exchanger in the opposite direction, hence the term counterflow. Of course, we need a superheat here, because even at the economizer port, we do not want to have liquid refrigerant or even refrigerant that has a low superheat, too low of a superheat entering that compressor. And also, when we're applying subcoolers, we have to remember that the expansion valve for the subcooler and the expansion valve for the evaporator, they're kind of, you could say, one impacts the other. So if one starts moving around a little bit and hunting, the other one likely will as well. So it's very important when we apply economizers like this that we have our superheat set for a pretty healthy value. In the instructions for years, BITZER has said, 10 degree Kelvin, which converts to 18 degrees Rankine, or Fahrenheit, if you will. So in this case, that's a fairly high superheat, and there's no problem having a high superheat going into the economizer port. In fact, that compressor could run it without the economizer altogether. So, but the idea is when you have a high superheat here, higher superheat generally brings a little more stability. We don't want that valve bouncing around and hunting, because we're going to have a problem over here in the evaporator with its expansion valve, inducing hunting at that point. But also when, again, if the superheats are too low, we tend to over dilute oil, and it reduces the lubrication value of the lubricant inside, specifically by reducing its viscosity. So if you look at, I didn't really bring it up when we were talking about capacity control, but there was a graphic that shows the slide valve, the rotors and everything all together. And you could see there's a port where the economizer feeds the economizer port of the compressor. That refrigerant goes in, it basically travels through the compressor housing internally and into the slide valve, okay? And these ports that you can see on the slide valve here allow for your economized, or the vapor leaving your economizer heat exchanger, to enter the compressor process. So unlike fixed unloading type compressors where their positions are fixed, slide valve is dynamic, you can move it around. The economizer port moves with the slide valve, so we don't have that limitation where, when you're economizing, you have to disable the economizer when your slide valve is running at a low capacity condition. So I wanted to bring that up because that's another feature of compressors in general that have slide valves. But with the BITZER compressors, all of the compact screws have this type of capacity control, this slide valve, this kind of economizing approach is used whenever desired. And this is also the case with semi-hermetic, the semi-hermetic BITZER screws that are the larger ones, specifically HS 85 series and beyond and larger. And same with the open drive screws, in fact, OS 85. So for, ammonia applications, HFC, same sort of thing. So. And that's all I had for today. I knew I didn't want to go too far with it because actually there's quite a bit more that could be covered in a compact screw presentation. But the purpose, again, as Sadie had mentioned, is to really cover the internal, the internals of the compact screw and show how it's integrated into the circuit and that sort of thing. So on this note, I've got my email here, the email address, and I'll leave this to you, Sadia, to open it up to questions, if there are any.
Hi, Phil. Yes, there are. We have a couple. One of them is, can the compact screw be installed in an outdoor unit?
Yes, the compact screw compressor can be installed in an outdoor unit. However, we just have to keep in mind that in this case, again, you've got a heater on the compressor and the heater needs to warm up that oil. But if the compressor is constantly exposed to very cold temperatures, then that heater may not be able to get caught up. On the smaller compressors, we use a 200 watt heater. Larger models, we use generally a 300 watt heater on there. And if it can't keep up, then we're going to have the same problem with refrigerant dilution of the oil. So when that compressor starts up, you've got a very low viscosity oil, you got a fair amount of refrigerant in there, may even see some foaming. It's just really hard on the compressor. So in these cases, it's recommended, particularly when a system's going to operate year round in an outdoor unit, that you heat and insulate the receiver just to ensure that we always have a good, healthy oil temperature for when that compressor starts up. Generally, when it runs, you've got a pretty good heat being formed, but it's a startup process each time that can be very hard on the compressor. And on the note of having outdoor condensing units with compact screws in them, another thing is that it may take some time to develop high side pressure or discharge pressure against that screw. And in that case, we have to keep in mind that the BITZER compact screws do not use oil pumps. They rely on differential pressure. And if you look at the envelope for the compressor, it'll indicate what the minimum saturated discharge temp is and maximum evaporating temperatures are. You've got to get in that envelope super quickly in order to ensure that that compressor operates in the envelope. So in a situation where you've got a compressor that's sending refrigerant into a stone cold condenser, it may take a bit for the pressures to increase. A discharge pressure regulator may even be required to enable the establishment of good discharge pressure on startup. So those are a couple of things to consider when putting compressor in an outdoor unit.
Okay, speaking of temperatures, what is the maximum allowable condensing temperature for the compact screws?
Maximum allowable condensing temperature. So as I mentioned before, the compressors can be used with different types of refrigerants. So when you get into lower pressure refrigerants, for example, 134A, R450A, R513A, refrigerants like that, lower pressure, you can generally go up to, I think it's around 140 degrees Fahrenheit. And then when you get into the higher pressure refrigerants, such as 404, 507, 407A, 448A, 449A, and the list goes on and on, it'll be approximately 140 Fahrenheit condensing. Or as compressor manufacturers, we generally talk in terms of saturated discharge temperature, because in theory, you could have a lot of pressure drop in your discharge line. And really, we have to consider what the compressor is actually seeing. So you could actually condense at a lower, you generally will condense at a slightly lower temperature than your saturated discharge temperature. So we just have to keep that in mind. Perhaps somewhat of a minor point, but yeah, so 140 for the lower pressure refrigerants, Fahrenheit, and then 120 Fahrenheit for the when you get into the higher pressure refrigerants.
Okay, and last question, is it more efficient to use the slide valve or a VFD to control the capacity of the compressor?
That's a good question, and it depends. So it really depends on the application for the compressor. If it really depends specifically on the load profile, I guess, because if the load is fairly high on a consistent basis, then actually installing a VFD it'll work against you in a sense that efficiency is going to be less through a VFD when you're running fully loaded most or all of the time. Definitely all the time. It's just going to be less efficient. Reason for that is the VFD is taking energy from the supply mains and converting it to an output. But in doing so, it absorbs its own power. So you're paying for that extra power, and it just shows up in the form of a loss. So in those cases, I would say that your slide valve is going to be more efficient. However, if you have a system that has a load profile such that it operates for extended periods of time at low load, then I'd say there's a good opportunity to install a VFD on that compressor. Again, it cannot be used with the slide valve at the same time. So if you're using a VFD, the slide valve gets driven to 100% position all the time, the entire time that the compressor is running. Okay, and so if you're running for low loads for extended periods of time, then a VFD can really, bring some savings to the table in that case. So that's why we, as compressor manufacturers, we're careful that, when you're promoting one technology, you're promoting capacity control. It really depends on the application. What does the system require? What is the load profile? So, but never use both, but depending on the load profile, maybe the slide valve is better if it's running loaded most of the time. If it's running through a wide range of capacities all the time, slide valve is great also in that case. But if you're running low load for longer periods of time, then again, the VFD, I think makes a little more sense.
Okay, great. Thank you, Phil. So this
welcome.
ends our presentation today. I hope our members found this informative. If you have any questions, please feel free to reach out to HRAI. Additionally, please complete the evaluation survey that will appear on your screen at the end of the webinar. And with that, have a good afternoon, everyone. And thanks again, Phil.
Thank you very much. Have a good day.
Bye.